So I got a comment like a year or two ago asking me how to tell the difference between fossils and pseudofossils or fake fossils. Now, spoiler alert, the one shown here is fake. In other words, it's not a real fossil. It doesn't represent life. So in this video, I'm going to be showing a bunch of examples like this one of pseudofossils and similar fossils that are actually real and how you might best tell the difference between the two. So first things first, what are fossils exactly? Well, fossils are just the remains of living organisms preserved in rocks, but there are a couple different types of fossils. Body fossils are those, like shown here, that are kind of preserved bodies of organisms, whereas trace fossils, the other major type of fossils, are things like burrow traces or footprints, traces of organisms, but not the actual body of the organism. Now, pseudofossils are just geological structures that resemble fossils or remnants of life, but are actually not. They form completely abiotically without the influence of life. For example, some are shown here on the slide. We have some belemnite fossils shown on the bottom left. These are just types of cephalopods from ancient Earth that can sometimes look like certain minerals. Like this is, I believe, tourmaline in a pegmatitic rock, and it's kind of showing a similar pattern to the belemnites preserved in this rock over here. But there are ways that we can tell them apart. One, the belemnites typically also preserve some internal structure, like these little white marks, and they have lines, horizontal lines going through them. And so that can be a giveaway. Another giveaway is tourmaline is a pegmatite, so you can kind of tell that it's in like an igneous type or pegmatitic rock, whereas fossils are mostly preserved in sedimentary rocks, primarily limestone. So by looking at the type of rock that it's in, that can give a good clue. And then also here's an example to the right of what are called septarian nodules, which are abiotically formed nodules or concretions of aragonite crystals, which are just calcium carbonate minerals. And these we can see over here kind of resemble egg fossils and have often been nicknamed dragon eggs when they're being sold at rock and mineral shows and stuff. And often they're kind of polished into the shape of the dragon egg. They don't typically look like that to begin with. So these are another one that not only kind of resemble fossils, in this case eggs, but also are marketed as fossils as well, which kind of exacerbates the problem of mistaking abiotic signatures as fossils. So the first major example of pseudofossils we'll talk about are concretions. Concretions are just rounded masses of mineral matter, and these can occur in many different sizes and form in many different ways. Typically, they involve the chemical precipitation, or basically formation of minerals, either as cement in between sediment grains or as concentric layers around a nucleus, like we can see here with the peloids. Ooids are like peloids, kind of just smaller, and they also kind of form this accretionary concentric growth around a nucleus. And what I mean by nucleus is like an organic or mineral grain fragment, basically. Any fragment that it, grabs onto and starts to precipitate minerals around, that's a nucleus. And that doesn't even have to be, that can be like a piece of plastic in these days, but any small tiny item. These ooids are really tiny. Here you can see the scale. It's 250 microns, which is, just really tiny. And these form typically in swash environments, so very shallow marine environments where waves are waxing and waning and rolling them over the substrate, kind of polishing their spherical structures as they precipitate that mineral, and that's why they turn out so round. And because of this polishing mechanism, they almost look kind of like pearls, but they're not. These are formed completely abiotically. Of course, they might form around something that was organic or biological, but their formation of the round spherical structure that is an ooid or a peloid is completely abiotic. There are, however, false or pseudo-oolites, or rocks containing ooids are oolites, And these false oolites often lack internal structure. So if you decide to go and look into, see if the rock you have is an oolite or not, you might cut it into a really thin slab and look at it under a microscope, because again, these are really tiny. And when you do so, you can either see this radial structure like over here to the right, or concentric layered structures. Those are all ooids around their little nucleus in the center. However, if they lack a nucleus and lack internal structure, they're probably not ooids. Either that or they're microtized ooids, which just means they've kind of been transformed or converted, recrystallized into micrite or just carbonate mud. But they can also, if they lack structure, be fecal pellets, which are biological. So those are technically fossils. And forms in which the origin is unknown are often called peloids. I think I said the peloids are the larger version of ooids. That's actually piezoids with an S, not an L. My bad. Peloid is when the origin of that little round ball is unknown. But ooids, pellets, and peloids and piezoids are not the only types of concretions out there. There's also manganese nodules, iron mochi marbles. I'm sorry if I'm pronouncing that wrong. These are kind of concretions that also can form concentric layers around either a nucleus, or sometimes they don't involve a nucleus. But I will talk about these iron concretions and these giant concretions shown on this side actually in a future video, because when I was looking into concretions, I found that they could get up to like several meters in diameter and be this like beautiful round structure still, and I was really intrigued by that. So I decided to make that a full video for the future. So I will, if it's out by now, I'll link it up here for you. If not, check it out in the coming weeks. But with that, I want to show a few things that are fossils that can sometimes look like concretions, or concretions can look like these fossils, which make them, easy to mix up. So here we have an example of a stromatolite on the bottom left. And stromatolites, the way that you might tell the difference between a stromatolite, or a round stromatolite in this case, and concretions is their waviness. As you can see, the internal layers of the stromatolite here are very wavy and crinkly, and the outer surface is very bumpy. That is characteristic of stromatolites. These are, preserved microbial mats, preserved layers of microbes on top of each other, and because they're microbial colonies, they tend to be very wavy. They tend to be this bumpy surface type morphology. So that's a giveaway for stromatolites. Eggs are something we talked about earlier that are often mistaken for septarian nodules, for example, but also can be mistaken for concretions and vice versa. So one thing that kind of gives away eggs is they often have their shell material preserved in a different mineral than the internal cavity of the egg was filled with. So sometimes that helps tell the difference, because you can kind of tell where the shell would have been. But if the shell isn't preserved, you can use the more oval shape to identify them, as well as the fact that they occur kind of in a bunch and then there's nothing around them, whereas concretions tend to occur, either very widespread or one-off. They're not, like a little bunch of eggs here and then that's it. Whereas eggs tend to occur in nests. So because of their occurrence like that, we can kind of use context to fill the gaps. Throughout this video, I'll talk a lot about context is key. So that's one way we can tell. Echinoids are another one over here to the right. These can be, they're radial often, because echinoderms all have either 5-side or radial symmetry. Because of that, they can be round, and that can make them seem like concretions. However, they often have intricate structures like the bumps on this echinoid or the details on this sand dollar here. So that can give away echinoids and other echinoderms. But if those get worn off, you have to kind of look for other features. They're a little bit smushed in comparison to most concretions, so that can be a giveaway. But again, sometimes it's just impossible to tell the difference and tell for sure that something is biological versus not. The next type of pseudofossil we'll talk about is tafoni or tafoni. I read these things, guys. I don't hear them being said very often, so I'm sorry if I'm mispronouncing it. But this is a beautiful honeycomb-like weathering pattern that is typically found in sandstone. And I have a weathering versus erosion video that talks all about the types of weathering, how they work, how erosion works, and how these types of things form. I didn't talk about this structure specifically in that video, but if you want to learn more about weathering in general, I recommend checking out that video. Basically, this honeycomb structure can often be mistaken for many different types of fossils, which I'll show in a couple slides. And another rock that can sometimes look a little bit like this honeycomb structure found in sandstone is actually scoria, which is not sandstone at all. It's not even sedimentary. It's actually a volcanic rock that forms with vesicles or kind of air bubbles in it because the lava that it cooled from had gas bubbles in it as it was cooling. And so that can often look like this tafoni as well. And I've gone to a rock shop. Fun story here. I've gone to a rock shop before where I found this really beautiful piece of this pinkish scoria. Oh, it was beautiful. And I mean, I could tell that it was scoria. Well, it wasn't actually scoria. It was more of closer to the top of the flow, of the lava flow, but not all the way up. So it has some vesicles. Wait, I should preface this. Most of the vesicle-rich volcanic rocks form at the top of the lava flow, and then the bottom of the lava flow is much less gas bubble-rich. So the scoria is up here, and in the center you might have some gas bubbles, some vesicles that form like this, but not a lot. And I think that's where my rock that I found came from, and it was just beautiful. But when I was checking out, I knew what it was, and the guy that ran the rock shop, obviously, he probably didn't know that I was a geologist. But as I was checking out, he said, "Oh, isn't that a beautiful sponge?" So I didn't say anything. I didn't want to be like, actually. So I just said, yeah, it's beautiful. Anyway, long story short, that's how I know that these things can be mistaken for fossils, but not just sponges, also burrows, or bryozoans, or corals, or worms. So let's look at a few of these. Well, here we can see some bryozoans on the left top images, which obviously you can see have a similar honeycomb structure in these branching forms, and then in this fan form can have kind of a net-like structure. The nice giveaway here is this fan-like or net-like structure on the very left has a clear, whitish color and is clearly kind of something laying over top of the rock rather than an internal weathering pattern of the rock. So that's a nice giveaway. Then if we look down here, we see a sponge fossil. This is an example of one. I mean, sponges can look so diverse, so it is hard sometimes when a sponge fossil is not preserved super well to see the pattern. But in most cases, you can tell the difference between things like scoria and tafoni with things like sponges, because sponges and corals and bryozoans tend to have a more regular, repetitive pattern in their little kind of cavities. Compared to tafoni and scoria, which are random, So here's an example. Actually, this to the bottom right, this tafoni to the bottom right, is, again, you can see how much more random it is compared to the actual coral fossil here. But this is actually what my quote-unquote sponge, my sponge scoria, looked a lot like. So I think that's why they thought it was a sponge, because it does look like, kind of sponge-like. So that's why. But I mean, it would have been even cooler if it had been, but I know it's not. And then here we can see some burrows that sometimes pattern themselves in a way that look like tafoni can. Here's another example with another picture of this tafoni or honeycomb-like pattern here in this outcrop. This kind of just shows how it might look from a different angle. It can kind of look straw-like almost, kind of like corals that are known as tabulates. These we often refer to as like bunches of straws held together. That's kind of what tabulate corals look like a lot. If you look up tabulate corals, you'll see what I'm talking about. But in any case, that can often be mistaken for that kind of tafoni from that angle. And then sponges, again, this is another sponge just from another, standpoint of their morphology that can look kind of like that honeycomb pattern, and then another, example of burrows, and also rhizoliths. Rhizoliths are kind of preserved root structures, and these don't often get preserved, but when they do, they can often have a structure that almost looks like a weathering pattern rather than fossils. Okay, so the last thing that can look a lot like tafoni, this one I don't have a clear trick for, but it's porous fossil bones. Fossil bones are, porous because bones are porous. And when they become preserved, they can look very irregularly porous, which makes them look a lot like a weathering pattern rather than something biological. I myself have been trained mostly in the art of identifying invertebrate fossils. So I've never dealt with looking at preserved bones per se, not from vertebrates at least. So I don't know how to recognize these in the field, and I might have come across one and not known it was a bone because I thought it was just an abiotic weathering pattern. So I don't have a good tell for this. What I can say is probably that, if the whole outcrop is in this pattern, this weathering pattern, it's probably not a bone. But if it's just a tiny little piece, then that might be. So I would say scale is the big thing here. Next we have lysogang rings. Look, guys, again, I read these things. I don't hear them said out loud very often. So I don't know if I'm pronouncing that right. I'm very sorry. But in any case, these are kind of concentric bands in rocks. And I think, at least when I looked these up and tried to learn about them for you guys, it seems like these are known to form in like gel-like media or solutions, but can also occur in porous sediment that provides a means for chemical diffusion. In other words, the diffusion of elements in a chemical reaction outward and inward in this ring structure, and the concentric patterns result from differential precipitation in the porous sediment media as the minerals precipitate in these ring patterns with different compositions. So what this means basically is maybe this circle with a little bit more of a red color compared to the more tan circles might have had more iron, dissolved iron, precipitate near that region or kind of coat those grains in that porous sand sediment media. Typically iron gives us like red staining, red or orange, so that's kind of why I think maybe these orange rings formed, and then the more tan ones and then the more orange ones was probably diffusion of iron and other elements. And then here in malachite we can see these rings with maybe more, copper, and then less copper, and whatever else is contributing to those light and dark green rings in malachite. In any case, obviously these rings can resemble fossils such as the most obvious one, which is tree rings. But because sandstone is typically the composition that these rings might occur in rocks, that's a dead giveaway because tree rings are not preserved in sandstone. They, if preserved, which is rare, they can be preserved in silica, but more rarely calcite or pyrite, but none of these are sandstone. They can also look a lot like stromatolites, or I guess stromatolites can look a lot like these rings. But the good thing about stromatolites is, one, again, they're wavy. So if we looked closely at these rings in this rock here, we would see that the internal layers are very wavy and crinkly because of the microbial mat structure that it was. And also, they're typically preserved in limestone rather than sandstone. And 3, carbonate isotopes can confirm whether something is stromatolitic or not, because the stromatolites represent ancient microbial mats, which were made up of, in large part, cyanobacteria that photosynthesized, and photosynthesizing organisms alter the carbon isotope composition of the rocks that they get preserved in because they take up preferentially light carbon isotopes. And I talk about this in other videos. I'll link one up to the top right. But in any case, this makes them identifiable. If we can't by physical features, we can do so by the chemical composition of the rock. Next, on to possibly my favorite, which is why I included it in the thumbnail for this video, dendritic features. Dendritic crystals or mineral coatings on rocks give a branching appearance that often is mistaken for fossilized plants. They actually form by manganese or iron oxide deposition on a rock's surface. However, another fun story, this video is full of fun stories. So when I took paleontology as an undergrad, we had a lab where we had to identify whether something was a rock or not and then kind of group it into its major group. In any case, in my class, we were given one of the things was a dendrite, and it looked a lot like this. And I remember we were supposed to, say, is it fossil or not? And every single person in my class, including myself, said that that was a plant fossil. And we were all dead wrong. And I couldn't believe that 100% of us, like nobody thought pseudofossil. I mean, they're named dendritic because that literally means tree-like. And that is what, they look like. So we all thought it was a plant. It turns out it wasn't. So I rate this pseudofossil as being like 10 out of 10, really highly possible to construe this as a fossil when it's not. I now, ever since that experience, will never do that again. But I feel like if you haven't come across this, it can easily be like, oh yeah, that's a fossil, but it's definitely not. The last type of pseudofossil features that I'll talk about include just general mineral habits. In other words, the kind of form or morphology or shape that minerals can take on. This is called a mineral habit. And there is a type of mineral habit called botryoidal. These are minerals that kind of look, I call them bubbly. Because they look very bubbly. I mean, look at this hematite here, and this is called grape agate, which is just botryoidal chalcedony, and it's beautiful and purple, and it's probably one of my favorite minerals. And then we've got pseudomalane, which is a manganese oxide mineral, I believe. And we've got mimetite, this yellow, beautiful bubble structure here. And then again, malachite, the green one we showed earlier. And then fluorite can be the structure. All of these minerals can typically occur in other types of habits as well, or shapes. But they can also be botryoidal or bubbly. And these can look a lot like fossils, or rather fossils sometimes can look like these minerals. For example, stromatolites can, again, like we talked about earlier, be bumpy, which is good because that separates them out from a lot of pseudofossils, but it actually makes them look more like these bubbly minerals. Another one is stromatoporoids, but stromatoporoids are more so bumpy, and if they are preserved on the top, this is the top facing us, and as well as the side, you can typically see on the side of the rock that there's a layering of the stromatoporoids. Same with stromatolites. If they're cut open in any way and you can see the internal structure, you can see the wavy layers inside, which is not the case for most botryoidal minerals, or if it is, it's much less perfect and smooth in fossils. It's more bumpy and irregular, especially in these microbial mat type fossils. Another one is coprolites, which are just fossilized poop, which can look bumpy and sometimes botryoidal, but they're not. So a dead giveaway here is mainly context. Again, fossils are preserved in sedimentary rocks, and most of these botryoidal minerals that I showed are typically formed in high temperature igneous or metamorphic conditions. So the giveaway is look at the main type of rock you're looking at, and if it's sedimentary, then it's probably a fossil. Acicular minerals are minerals that are actually super cool. A lot of really cool structures are made with acicular minerals. Basically, they're a mineral habit that looks kind of needle-like or hair-like. The term actually comes from the late Latin meaning of little needle. Really, honestly, the radial acicular minerals here don't look like much, if anything, maybe sea urchins, but sea urchins are echinoids, like I showed earlier, and so typically their bumps get preserved and their patterns get preserved and their round shape, but not their spikes. So typically, acicular minerals, although they look like something that could be hair-like or fossil-like, they're completely not. There's also fibrous and filiform minerals and also different acicular forms of minerals that can often look hair-like, and this could be mistaken for like fossilized hair, I suppose, but the giveaway here is most of the time animal hair or fur does not normally get preserved because it's just organic and it gets broken down so quickly. So in the cases where it is typically only in frozen preservation, where you have everything preserved in frozen ice, then you can kind of get your insight into whether it's real fossil hair or not by looking at context. Is it frozen or is it not? Is it igneous or metamorphic or is it sedimentary? So again, context is key here. Agates are kind of a mineral habit, but they're also a type of mineral. They're actually a variety of chalcedony, which is a cryptocrystalline variety of quartz, which have this intricate banding. Basically, any type of chalcedony that has this, beautiful banding is technically an agate. They form when silica-rich fluids fill cavities in either volcanic or sedimentary rocks, and then cool, evaporate, and precipitate silica minerals in layered bands. The colors come from impurities in the silica, typically things like iron, manganese, or other metals. Really, there's no fossil that is often mistaken for agates. I think the only reason they might be mistaken is if the layers turn out to look like something biological, but really they are just these bright, beautiful, colorful, completely abiotic chemical precipitates that turn out to be really beautiful. But there are things like agatized bone fossils, in which case you're not going to get those layers, but you are going to get maybe tiny little agates preserved in the pores of a fossil bone, and sometimes things like wood, petrified wood. So, you can get agates or agate replaced fossils rather, but they don't really look anything like layered agates. Stalactites and stalagmites can also be a mineral habit, not only in caves, but in also other formation environments. Stalactitic mineral habits can form, and they also form completely by abiotic chemical precipitation, so not a fossil, but like I talked about earlier, some coral fossils, typically tabulate corals, can look like straw-like structures like this. And so sometimes they can look similar to stalactites, but they're really not. And you can tell the difference. I mean, that really has a lot of structure to it. If you were to zoom in or look closer at that fossil, you could see little structured horizontal partitions on those, and at the top they each have like a polyp cavity. So really they don't look that much like stalactites, just superficially at glance maybe. Next, we have tektites. Tektites are glassy minerals that result from impacts. They form when extreme heat and pressure generated by meteorite impacts melts like the impactor material, the Earth's surface material, everything in that vicinity, and ejects a bunch of material into the atmosphere. And when this material, which is molten at the time that it's ejected, falls back to the ground from the atmosphere, it cools and solidifies in like a teardrop or more aerodynamic shape, which can make it look like things like, maybe that could be mistaken for a coprolite or maybe even a belemnite. Belemnites are those kind of aerodynamic type shapes I showed at the beginning. They're a type of cephalopod that lived a long time ago, kind of look like bullets in some cases, but again, typically composition is either silica or calcitic, so they're not volcanic, so they're not often mistaken for tektites. The last one I want to talk about is my favorite example of a pseudofossil because it actually for a while was mistaken for the fossil that represents the first life on Earth, which was pretty crazy. It, spoiler alert, was not. Now we know that. But this was named, it was given like a species name, Azun canadense. I'm not exactly sure how to pronounce it, but it means the dawn animal of Canada. It was found in Canada. Initially, the guy who found this and described it in 1865, John William Dawson, described it as a giant foraminifera. These foraminifera are these types of microfossils microfossils, also microorganisms that still exist today and have all these different morphologies. So he just called it a foram. He wasn't sure exactly what kind it was, but it had this tiny layering that made it look a little bit like the internal structures of some forams. Because he called it a fossil, that made it the oldest known fossil at the time. And the banding, now we know, is actually just crystalline calcite and serpentine and forms completely abiotically. It was found in 1894 that it was all associated with metamorphism and that high temperature processes were actually responsible for its formation. So it wasn't actually a species of life. It was a species of chemical precipitation. So stromatolites over here on the left have thin layering like we've shown throughout the video and can sometimes have this bumpy fingernail-y look to them that the Azoon canadense had down here in its structure. And then fusilids have internal layers that look a little bit like that. They're a type of foram, but you know, really they're much more structured. And then this kind of echinoderm here, Helicoplacoidea, this echinoderm is, I think, the most similar to this chemical precipitate, but it does have, as you can see, kind of more regular structure than the Azoon canadense. But before you guys jump off the video, you might be wondering, why do we care? It's obviously interesting to study and distinguish between pseudofossils and fossils, but why do we need to? It's actually really important that we can tell the difference between real remnants of life and not remnants of life, because one, it helps in the search for extraterrestrial life on other worlds, because if we know, for example, Martian blueberries were found to represent the ancient presence of water on Mars, because we know their formation requires water, and there's some evidence that shows their formation might also involve microbes. And so if we study these types of structures more, we can get a better idea what the requirements are for certain structures, and if they require life, then finding them on other worlds might mean that there either was or is still life on those worlds. Now, don't get your hopes up. Martian blueberries or iron concretions can form abiotically. But the other reason that it's really important that we study the difference between pseudo and real fossils is for early life on Earth. Again, we need to know if what we're looking at is a fossil or not, because we might make a claim like, look, here's the oldest fossil ever. Life evolved longer ago than we originally thought. But like I just showed, in the 1800s, we made that claim with the pseudofossil and had to retract it later on. So we have to be really careful about knowing what we're looking at and knowing that what we're looking at is a fossil before we say that. So I hope you guys enjoyed learning about the differences between pseudo and real fossils and are now excited to go out there to the field and look at and recognize those for yourself and those differences that we talked about. There's some really cool minerals out there that just look like so cool that they would have had to involve life but didn't, which kind of makes them even cooler. But in any case, yeah, I hope you guys have fun exploring, and I will see you guys in the next video. Bye.